Thank you very much. Good morning, everybody. I know we're a little bit behind on the schedule, so I'm going to try and make up a little bit of time here. I have a relatively short presentation. Again, my name is Ron Keith, and I am the Chief Operating Officer of Sanctuary AI. I'm going to start with a little bit about Sanctuary. Sanctuary is a relatively young company. We were founded and are based in Vancouver, Canada, in beautiful British Columbia. So if anybody's looking for a job in Canada, please come see me after the presentation. We focus on embodied AI. Specifically, we are a designer and manufacturer of general purpose robotics, general purpose humanoid robotics. And those are enabled with dexterous hands. Hands happens to be the topic I'm going to talk about today. We're considered an R&D leader in our field. We have a larger intellectual property portfolio than any other startup in the field, and we're going to talk a little bit about our intellectual property here in a few minutes. So the humanoid opportunity is really about the developing labor shortage, and specifically the developing labor shortage in the industrialized world. The industrialized world is getting older, and let me take a quick survey here of the audience. How many people in the audience are getting older? 3 people. Wow, there are 3 people in the audience that are getting older. Most of the industrialized countries are getting older, and what that means is there are more people that are dependent on people in the workforce and less people that are actually participating in the workforce. If you look at Japan, for example, Japan in 1990, there were 43 dependents that were not of working age. They were either older or younger than working age that were dependent upon people in the workforce. Today in Japan, that same number is 70. There are 70 people dependent on every 100 workers. And this is an age-related problem, and it's something that's happening throughout the industrialized world. On top of the age-related problem that we have with the aging of the industrial world, we also have a multi-decade decline in labor force participation. This is global data, the source is the World Bank, and this is the number of people that are of working age that are actually working across the world. It's about 62%. This number is expected to decline to about 60% globally over the next 10 years. So the humanoid opportunity is really about enhancing labor and replacing labor in the factories as people age out of these jobs. In the United States, the average worker makes about $35 per hour today. That number has gone up about 2.6% per year over the last 20 years. It's probably going to go up 2.5% to 3% a year over the next 20 years. So we're looking at 20 years from now, labor in the United States being about $61. According to research firm Korn Ferry International, the cost of humanoid robotics is going to come down, as does most technology, at a very steep rate. They're suggesting that the cost of deploying humanoid robots is going to come down by 10x every 8 years over the next 25 years. What that means is in 6 or 7 years, we're going to have labor that's $50 an hour, and we're going to be able to deploy humanoid robots for $5 an hour. So we need intelligent, flexible, dexterous robots. This isn't a dream, this is an actual need for society. So when we talk about enhancing the global workforce, there's one common factor that the global workforce has. And the global workforce is about 2.6 billion people. Almost all of those people have hands. And human labor is designed around the human hand. And the human hand is very challenging. So when I'm talking about the challenges that we've faced at Sanctuary that are being faced by other humanoid companies, one of the ones I'm going to talk about today, or the primary one, is about making dexterous hands. So the underlying challenges with that are many. One is power density. The human hand is quite strong. It has many different grasps and many different affordances of those grasps that require quite a bit of strength. Even if it's something as simple as taking the cap off of a water bottle, there's a lot of strength in the human hand, and that's very difficult to mimic. When you look at power density and you look at the size of the human hand and all of the motions, there's a lack of commercially off-the-shelf available components to make some of the miniature mechanisms to come up with an anthropomorphic hand. Kinematic mapping. Kinematic mapping, mostly as it relates to teleoperations and policy training via teleoperations, is a significant challenge. Then the level of dexterity. I think the human hand has 27 degrees of freedom. It's a very complex mechanism, and mimicking that requires very sophisticated mechanisms. And then, of course, tactile sensing. Our skin is a remarkable set of sensors, and being able to mirror that is very, very important in terms of enabling human-like dexterity. So at Sanctuary, over the last 6 years, we've developed 5 different generations of anthropomorphic hands. We've basically tried everything. We've tried direct electromechanical actuation, we've tried cables, we've tried hydraulics, and it's our assessment that hydraulics is the only technology that can provide the right combination of strength, speed, and controls. This curve here is showing, on the vertical axis you've got speed of motion, on the horizontal axis you've got force, and you can see these are different electromechanical actuators that we've tried in various hands. You can get fairly good speeds with direct EM, but relatively weak on force. But if you look at the curve for hydraulics, you can get very good speeds and very high levels of force. So the current electromechanical actuators really fail on the power density. They're pretty good on the control side, but you just currently can't get the amount of power density out of electromechanical or cable actuation. Now, the hydraulics need to be miniaturized, and that creates some different problems. This is a slightly different graph, but also talking about the need for hydraulics. So this is grasp strength, this is degrees of freedom. As you get more and more degrees of freedom and start to approach the number of degrees of freedom in the human hand, what we see is you can't get enough power density in that space to mimic human strength. Whereas in hydraulics, you can far exceed the human strength requirement because the density that you can get out of the design is far greater. So in terms of power density, DC motors, maybe they're 250 watts per kilogram, which is about half of what human muscle is, about 500 watts per kilogram. Hydraulics, obviously depending on the pressure, flow rates, etc., is more like 2,000 watts per kilogram. But taking advantage of hydraulics in a form factor like the human hand presents some challenges of its own. So we've had to design a whole set of miniature hydraulics for our human hands. One of the most important enabling technologies that we've developed are control valves to control the flow to each individual digit and each individual degree of freedom. If we look at off-the-shelf components for doing that, certainly there are no lack of off-the-shelf valves, but these are very big valves. Most hydraulics are not made for miniaturized applications. And so the valves that were available to us were like 5,000 watts per pair. And they'd make a set of hands that are like this big. So we designed our own valves. They're about 8 times faster in flow actuation, about 6 times cheaper. And we have tested these, we have tested these to 2 billion actuations without failure and more than 1 million valve cycles without any leakage. This is the current, this is a double-acting piezoelectric valve, hydraulic valve that we've designed. This controls all of the degrees of freedom in our current hand. Our current hand is 22 degrees of freedom, so we have 22 of these double-acting valves in the hand. We were forced into designing this because we couldn't find anything like this off the shelf. What we designed is about 7% of the volume of what we could find off the shelf. And because we designed it ourselves, the precision, the fidelity, and the controls are optimized specifically for the robotic hand application that we have. And again, we have tested this to 2 billion cycles. that is a very big challenge in humanoid robotics is the fact that, especially in hands and dexterous hands, is a lot of the components are just not available commercially off the shelf. If you think about the hand, it's kind of a really big Swiss watch. And so it's not just the hydraulics that are challenging to find off the shelf. So the lack of commercially available off-the-shelf parts is probably the second biggest challenge that we face. And it's everything. I mean, we find that we have to design miniature bushings for each knuckle because we can't get the type of durability and reliability that we need on off-the-shelf components. Sometimes we have to design our own bearings, our own couplers, and of course, tactile sensors. So again, if you can't buy it, you're forced into designing it yourself. Part of designing it yourself means you generate a lot of intellectual property. This particular chart, this is not a company chart, this is from a company called PatentVest in one of their recent reports. And they say that Sanctuary AI has the largest intellectual property portfolio of any of the humanoid robot startups. And some of the companies they're comparing us to aren't exactly startups. I see Tesla's on here. But according to this report, we actually have more intellectual property or a bigger intellectual property portfolio than all of the other humanoid combined. And part of that is because of this necessity to design things when we can't find. If we break down that into different categories, the general purpose robotics category, software, fleet management, training, and things like that, we come in third. Now, this is behind companies like Alphabet, so, you know, they're not exactly a startup. And then on dexterous manipulation, we come in fourth. On dexterous manipulation, we also come in fourth, but the overall strength of our portfolio is far in excess of what we see from our competitors. So the next problem with dexterity is the kinematic mapping. Most of the policy development that we do through teleops training. So we have robot pilots, they wear haptic gloves, we use cameras, we use exoskeletons for doing this. But the problem is all hands are different. And when we move our hands, we don't really think about the joint angles and things like that. In our control system, the human control system automatically knows how to do this, but the robotic control system doesn't. So there's some kinematic mapping that needs to take place to enable this. So this video is basically showing the kinematic mapping of the robot hand, where what we're looking at is the end point of each finger. But the end point of the finger isn't particularly valuable from a controls perspective, because what you need to know from a controls perspective is the joint angles and things like that. So you need to be able to tell the motors how far to move, in what method to move, et cetera. I'll try and go through this fairly quickly, but this is the challenge. So in hand mapping, you start with the human motion of the hand. Then you have to have a motion capture system, and then you have to do some kinematic mapping or kinematic matching of what the motion capture device sees versus the actual hand position, the hand angles and stuff like that, to get from the position of where the end of the fingers are to the actual angles of the joints and stuff. You have to use inverse kinematics. Once you have those inverse kinematics, then you have the controls issues of telling the robot, where do I take the abduction angle on this finger, or things like that. And then you also have the robot dynamics, which would be things like, you know, latency, backlash, things like that. This is a test bench where we're just demonstrating the mapping of our. If you look, the robot pilot has some fairly sophisticated haptic gloves that have about 70 different sensors in them. Now, the problem with kinematic mapping and inverse kinematics becomes a lot less if what you're doing is simulation training as opposed to using teleops for doing your policy training. Here, what we've done is we've done the simulation training using the CAD data. And what we're doing is in-hand reorientation or in-hand manipulation. So I think there are about 40,000 simulations going on here, and then this is the manifestation of it, or the actual reality of the reinforcement learning training. This is my favorite video. So we were talking about hydraulics and it being the only path to human-like strength. Here what we're going to see is we're going to take a 5-kilogram weight. We're going to attach it to the bottom of this cylinder. The robotic arm or the robotic hand is going to hold that upside down and do in-hand reorientation in a circular motion. I promise you 90% of the people in this room cannot do this. And there are no EM hands that can do something like this. I'm going to play that one more time. Oops. Or maybe not. Five kilograms is a lot of weight to hold upside down and then try and spin something like this in your hand. I'm having a hard time doing it with my remote. So the last challenge with hands in achieving human-like dexterity is the sensors. It's the tactility, it's basically the touch, if you will, that allows you to manipulate objects. To do that, you've got the touch sensitivity. That's an important issue. You've got the durability of those sensors. You've got the coverage of those sensors. And of course, the latency that those sensors may introduce. And then feedback to teleops. So here's a demonstration of our in-house made touch sensors. Again, there's kind of a theme here. If we can't find it off the shelf, we have to go design it and manufacture it ourselves. What this is a test bench that's been told to move until you touch the domino and then stop without knocking the domino over. When people come through to get tours of our facility, we show them this and we ask people to try this themselves. Most people, if they close their eyes, cannot do this task. Now, if they have their eyes open, they can do the task. It's a combination of the visual and the touch. But the challenge with having these sensors is for them to be really sensitive, they also have to be durable. So this is what some of our sensors look like after having inserted some screws into a crankcase for one of our customers. So you see they're a little bit tore up, so this is a big challenge that we continue to work for. You know, replicating the sensitivity of human skin is a real material science challenge. So with that, I'll leave you with this last video where you can actually see the sensors, our touch sensors in action. Thank you.
Thank you. Thank you.